Another group of chemical sedimentary rocks are the evaporites. So many areas that are now dry land used to be shallow marine bays with only a narrow connection to the ocean, to the open ocean. Under these conditions, seawater could move into the bay to replace some of the water that was lost to evaporation, which eventually the water of the bay itself became saturated with salt and other ions that were forming. And so these deposits ended up remaining, and hence why we call them evaporites. Minerals that precipitate in this fashion are halite and gypsum, for example, which is anhydrous calcium sulfate. The former being the main component of the rock salt, and the second making the major component of the rock gypsum. Salt is very key for cuisine, melting properties, and for making hydrochloric acid, for example. Gypsum is used for plaster and for drywall. Gypsum starts precipitating out of solution when 80% of the water was evaporated. Halite when about 90% of the water was evaporated. Okay, so gypsum 80%, halite 90%. Places like the Bonneville salt flats in Utah are good examples of this. Or, for example, in Carlsbad in New Mexico, layers of gypsum and anhydrite, which is a non-hydrous type of gypsum, are intermixed. The salt dunes of New Mexico are also good examples of this, and the salt sea in Bolivia, which is the picture on the top right, are fantastic examples of where you can find evaporites. Okay, so we just finished covering chemical and biochemical sedimentary rocks, and so now we move on to organic sedimentary rocks, which is the last category that we have. Okay, so for organic sedimentary rocks, let me change that. So for organic sedimentary rocks, we have coal, basically, and the derivations of coal. So coal, unlike calcite and silica or evaporites, is made almost solely of organic matter. Close examinations of it typically reveal some plant matter, such as leaves, bark, and wood that have been chemically altered, but that are still identifiable. This supports that coal is organic material that was buried and preserved from millions of years ago. The formation of coal involves, I should say, a few stages. And the first one is the accumulation of plant remains. Here, large quantities of organic matter accumulates first. This should be decaying in an oxygen-poor environment where oxidation cannot complete the decay of that plant matter. Places like swamp are good environments for this to occur. The plant decay is driven by bacteria here that liberate the hydrogen and the oxygen so that the carbon content becomes greater as a percentage. Later, that bacteria cannot continue their decomposing job due to the acids that are liberated from the plants. So, second thing that occurs is the formation of peat. The first step leads to the creation of peat itself, which is a soft brown material in which plant structures are still easily recognized. So that's going to be this right here. Later, with extra burial, peat becomes into lignite, which is a soft brown coal. So this is lignite right here. Formation of this lignite and further of bituminous coal is going to be the third step. So at higher temperatures brought by burial, these are going to lead to chemical reactions within the plant materials and yield water and organic gases. So those are going to be volatiles. With further burial and weight on top of that lignite and on the sides, the gases are going to be driven out, and hence the proportion of the carbon within that sample increases. With burial, there is also a compaction into a new harder form of coal called bituminous coal, which is a black and soft still, but it's going to be more compact and denser. The compaction is so great in this step that a layer of bituminous coal can be 1/10 the thickness of the lignite from where it came. Okay, the fourth step is the formation of anthracite coal. When these sedimentary rocks, as are lignite or bituminous coal, are exposed to folding and deformation associated with mountain building, the heat and the pressure cause further loss of those volatiles and that water, thus increasing the concentration of the fixed carbon. This metamorphoses the bituminous coal into anthracite, which is a jet black and shiny, but still not as dense metamorphic type of rock. Anthracite is hard to find and also hard to extract, so not much of it is used for energy producing purposes as opposed to bituminous coal and lignite. Okay. So, some of you know coal is a major energy producing resource that is non-renewable. And some of the problems associated with burning it will be discussed later in the lecture. But the map below shows the different coal types that can be found and are mined in the US. All right, so with that, we have covered the triidal chemical, biochemical, and also organic sedimentary rocks. So we will move into diagenesis and the lithification process. So thus far, I've told you that sediments change as they are converted to sedimentary rocks. The term diagenesis is a collective term for all chemical, physical, and biological changes that take place after the sediments are deposited and during and after lithification to form a sedimentary rock. So I think I told you earlier in the lecture that diagenesis happened from the time of weathering. Excuse me, I was a little bit wrong. So it's from the time of deposition. So diagenesis doesn't involve any changes that occur, for example, in transportation. They have to occur after deposition of that rock. Okay, so let's talk about this diagenesis a little bit more. With burial, diagenesis is usually promoted. As sediments are buried and subject to the increasing temperatures and pressures, this process occurs within the upper few kilometers of Earth's crust, and the temperatures will generally be less than 150 to 200 degrees Celsius for diagenesis to occur. Once that the temperatures reach these threshold of 150 to 200 degrees C, depending, there will no longer be changes that involve sedimentary rocks, but there will be metamorphism occurring, so changing the rock into a metamorphic rock, which we will cover in chapter 8. One example of diagenic change is recrystallization, which is the development of more stable minerals from less stable ones. An example is the transformation of peat into lignite and bituminous coal, for example, as we saw in the last slide. Or another one is the recrystallization of the mineral aragonite, which we haven't looked at. Aragonite is secreted by many marine organisms, just like the calcium carbonate was, for example, in the chalk. But aragonite is a less stable mineral, so aragonite ends up turning into calcite in those marine environments, recrystallizing into calcite. So diagenesis itself includes lithification within its process, as well as recrystallization, which is lithification, I should say, is the process by which unconsolidated sediments overall are transformed into solid sedimentary rocks. So lithification is going to include two different things, those being compaction and cementation. So for compaction, as I told you earlier when we were talking about shale, is going to be the process by which the pore spaces in between the sediments are reduced by the overlying and confining weight. So the deeper a sediment layer is buried, the further compaction that there will be, and hence the less pore spaces that are filled with water or with air. For example, clays may reduce by up to 40% in volume after compaction occurs. Sedimentation, which is the second process of lithification, is the most important process of the two. And in this process, the sediments are converted into sedimentary rocks. Here, ions are carried in solution by the groundwater, and they crystallize in the spaces between sediment grains to form minerals that gradually will cement those grains together. Just like compaction, this process will end up reducing the rock's porosity. So all those pores that were initially filled with air or water are now filled with minerals that crystallized. So it reduces the rock's porosity. Calcite, silica, and iron oxides are the most common cements, and it is relatively simple to identify these cements from one another. Calcite will effervesce in contact with dilute hydrochloric acid, so it's easy to tell whether a rock has that type of cement. Silica is hard and it's unreactive, and then the orange and dark red color in sedimentary rocks means that iron oxides are present usually in the cement. So they're fairly easy to tell apart. Crystalline sedimentary rocks like evaporites are often lack the pore spaces in between any sort of crystal, because those crystals grow until they fill all of the available space. So they will be relatively impermeable to any fluids such as water or oil. So they don't necessarily need any sort of cement because those crystals filled in that space in between and hence won't allow any water rich with ions to flow through them. All right, so now we'll briefly look at the classification chart for the different sedimentary rocks. I split the chart into two so that the detrital sedimentary rocks are in this slide and the chemical, biochemical, and the organic sedimentary rocks are in the next slide. So this is figure 7.20 out of your book in case you're curious and want to check it out. So we see that the detrital sedimentary rocks are split on the basis of particle size primarily, as I had said before, whereas the primary basis for the classification of the chemical groups is their mineral composition, as you'll see in the next slide. So the classification chart here presented is perhaps more rigid than the actual natural phenomena, as most cases in nature. And I should say not just the chart for the chemical and organic sedimentary rocks, but also the one for the detrital sedimentary rocks, okay? So in reality, some of the chemical sedimentary rocks contain some small quantities of the detrital sedimentary rocks, and conversely, detrital sedimentary rocks usually are cemented by chemically driven cements. So in truth, they are also partly chemical sedimentary rocks. As you can see in the charts, and by the description of the main sedimentary rocks that we went through in the last few slides, there are many types of sedimentary rocks. Some are termed clastic, meaning with fragments. All detrital sedimentary sedimentary rocks are going to be clastic, and some of the chemical ones will too. For example, coquina or oolitic limestone, for example, are clastic because they have some sort of fragments that make them up. And some other sedimentary rocks are non-clastic, for example, chalk or travertine. Others, like evaporites and chert, are called crystalline rocks, and hence may sometimes resemble igneous rocks, for example. They differ in mineral composition very greatly from any type of igneous rock, however, so they are easy to separate from them. So again, within these chart, we have three main sort of sub-classifications, which I'm not going to quiz you on this, but it's just terms that are used for the types of sedimentary rocks. One of them being clastic, meaning having fragments. So both detrital and chemical rocks can be clastic. It can be non-clastic, again, like chalk or travertine, or it can be crystalline, like evaporites or chert.